Welcome everyone to today's live stream. We have Luke Wriglesworth talking about finding fractional dimensions, traces of fractional dimensions in galaxy data.
Exciting. Welcome, Luke.
All right, I will share my screen. Yeah, so I was a student at Wolfram Summer School in June and July this summer. And the project I worked on, it was basically finding a way to measure how distributions of galaxies scale with volume. So I did that using basically hundreds of expanding spheres. And I'll talk more about that, but I'll start off just with my data set because that was like half of the project, just getting that up and running. So everything I used, it was from HyperLEDA. So HyperLEDA, it is basically a compilation of many galaxy surveys and like from research papers and stuff like that. So for each galaxy, you'll have like six measurements, and what I did, I used the SQL query, and I just got the mean value of the measurements that I needed for the whole data set.
Which SQL query did you use? Was that the SQL there?
Yeah, yeah. Here. I don't remember what I typed in, but
Okay.
yeah. Yeah, so I got it from there. You can download it with the SQL query form, or I also posted the file on Google Drive, so you can just download it directly. But I imported it. I got the coordinates, latitude and longitude, in the galactic coordinate frame, and they also have a column for redshifts. So that is in the column V. So to actually get the redshifts, you divide everything by the speed of light in kilometers per second. Yeah. So the next thing you need to do, you need to get the distances to all the galaxies. And I got the co-moving distance. But first, since we're using redshifts to calculate distance, I had to make sure there's no negative redshifts. So here I'm just getting the fraction of negative redshift galaxies in the data set. And I
But what
just,
does that mean exactly, negative redshift? They're blue
it,
shifted?
it basically, it's like super close galaxies. So they're like moving towards you, I guess.
Hmm.
Yeah.
Like in a
So
local cluster or something like that. So
yeah,
they're,
they're like
they're
the closest galaxies.
mhm.
So here I just removed them. There's only 97 out of like 2.8 million.
Mhm.
So not too significant. Um, and then the way you get the co-moving distance, I use the lambda cold dark matter model. And this is actually really easy in Wolfram language because there's this handy function. It's called universe model data. And I think there's like four different cosmology models you can choose. But yeah, you just input your parameters and redshifts, and then it will spit out like whatever information you want, basically. There's tons of stuff here. Um, yeah, so I used the default parameters with a few overridden just because it was recommended in the HyperLEDA documentation. So I'm not sure what the default values are for this function, but I overrode the Hubble constant, the dark matter, or yeah, this is just the matter density constant, and then the dark energy constant. So yeah, using this function, I defined like just the distance function. So you just input redshift, and then it outputs co-moving distance. So yeah, I applied this to the whole redshifts column, and you get all these distances. So most of them are within 10 to the 10 light years, and there's a few outlying ones. The edge of the visible universe is like 4.6 times 10 to the 10, and our furthest galaxy is 2.9. So we're still within the range. Yeah, so next I went ahead and
So
visualized
this is
it.
after correcting for cosmological effects.
Uh, so this is basically all I did. So the way
Right.
this works, yeah, calculations use Friedman. Da, 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 da. So yeah, this is all I did to get distances.
Okay. So that's
Um,
measuring like the proper distance after the space in between is expanded over,
oh
however long
yeah,
it is.
oh yeah. So
And it's
this is co-moving
approximating
distance.
the distance based on the redshift, and the Hubble
Yeah,
law, and
so
all that stuff.
yeah, so the co-moving distance, it's like the distance that remains constant in time. If you like, it's the distance with the universe expansion factored out, basically. So yeah, it is not the proper distance.
Oh,
Yeah.
okay.
Yeah, so co-moving distance is basically I think I put like a GIF here. But it's basically as if the coordinate system is expanding like at the same rate as the universe. So it's just like a visualization. So it basically remains constant in time. Yeah, so next I went ahead and visualized everything. So here I'm just creating like a color scale based on the redshift. Um, uh, Yeah, and then here I plot it on like a 2D map projection. So it comes out looking like this. And basically, the more red it is, the further away the galaxy is. And this is in the galactic frame. So down the horizontal line, that is the Milky Way disk, basically. That's why there's like barely any points, just because it's not easily visible.
That's
Uh,
interesting. So a lot of this comes from like these surveys that are
yeah, yeah.
search out whole bands of the sky.
Mm-hmm. Yeah,
I
yeah,
was
yeah.
gonna ask.
It's
Oh,
it's
sorry.
very clustered in like random locations.
Okay. So that's what those strips are, is because that's where there is data that was
Yeah,
scanned by satellites or what.
yeah. So like the data I use, it's like a compilation of like tons of different separate surveys. So like yeah, like someone went ahead and like surveyed just this spot basically and ignored
And when you
everything.
say survey, what does it actually mean? Is that data was collected with like terrestrial telescopes or satellite arrays? What?
Yeah, they use like radio telescopes, I think. I'm not too familiar with all the instrumentation, but I think that there's like a large amount of different ways you
And just to
can.
get a feel for what's going on here, so is every dot a galaxy?
Yeah, yeah. Every tiny dot is a galaxy, and there's like
That's
2.8
crazy.
million points.
That's crazy.
Yeah. So yeah, so for the type of analysis I wanted to do, spherical coordinates is not very convenient. So what I wanted to do, I wanted to lay out the spheres in like a giant grid. So next I converted everything to Cartesian coordinates. So here I just do like a coordinate transformation. Um, yeah, and then I went ahead and plotted it in 3D Cartesian, and it looks like this. It's very laggy.
Well, I
But
guess
yeah.
you need a GPU to render this in real time, as you say.
Yeah, yeah. Yeah, it's very intense.
That is epic.
Yeah, the whole project it uses like 20 gigabytes of RAM, like on average when I was working on it.
So there's also a couple. Okay, I want to ask a couple questions here. So the concentration of galaxies that are closer, is that a product of the areas that happen to have been scanned? Like
Um,
what gives it that shape? That's just the data that we
so
have.
this is just, it's obviously like biased, because just based on like what we're capable of observing. So like the closer galaxies will have been like discovered first, and they're easier to find basically. And also, this survey, it's only like confirmed galaxies. So to actually like complete the project and get like good measurements, you would need like way more galaxies than this. So this is just like a tiny, tiny fraction of the actual galaxies that are out there.
And then also to identify some more stuff here. So that kind of band that's in the bottom left quadrant, is that Milky Way
Yeah, that's
tail
the
that's blocking?
yeah, that's the gap that you see here in 2D. So
Very cool.
yeah, so I plotted it in 3D, and this is just another interesting thing. So we were just messing around we're using like machine learning clustering algorithms, and this is just one of the clusters we picked out. We didn't use it for anything, but it just looks cool.
So you ran a machine learning clustering
Yeah,
algorithm.
this is from the DBScan algorithm that's built into Wolfram language.
And what is it doing? Is that just projecting that 3D space into 2D space? Is it like a
I actually don't know what it's doing. That was kind of like the problem why we didn't want to go ahead and use it, because like Steven said, like we don't really know like what
what to
is
say about it? Yeah,
prioritizing, like why is it picking out these bands, but yeah,
it looks awesome though.
but it
It's
looks
very
really
cool.
cool.
Yeah.
Yeah. Yeah, so now we have a working data set, and we can go ahead and actually do the measurements. So yeah, the whole idea is that if you have a sphere and you place it into like a dense space full of points, and you grow the sphere, and as you're growing it, you count the number of points within the radius r of the sphere. It should grow proportionally to r cubed, and the derivative, the rate of change, or the number of new points you encounter at each time step, that should grow like r squared. And yeah, so this is my code for doing this in just a single sphere. So yeah, and also yeah, I have a minimum galaxy count here just because I found, just through trial and error, I needed at least like 300 galaxies just to get it to fit a line to the function. Otherwise, I was getting like tons of errors, and it wasn't good. So that's what this is for. Um, so here's a visualization. So this would be the outer radius, and then there's the starting radius would be half the radius of the sphere. So all the code does, it just counts the points at the radius r as you grow from like half this radius to the full radius. And if you plot it on like a log plot, you just get a line with a slope of 3. So it just spits out the exponent here. So we get 2.98 for the exponent for n of r, and then 2.0 for the derivative. Yeah, I think that's all for that.
So is this log plot showing the scaling law? Normally it's plotted like that way, but the numbers are going bigger, going down here. But
Um, yeah,
okay,
yeah,
What?
like log of r, log of n of r.
No, they're getting bigger on the positive axis for each dimension. But in
Okay,
any
yeah.
case, yeah. So that makes
so I mean, the point is, it is scale invariant or it's not scale invariant?
What do you mean?
yeah, normally when they do log plots, they're showing that regardless of how big things get, it will always get bigger in either dimension.
Mhm.
Even bigger. Yeah, it's not a normal distribution at all, basically. It's the point of
Yeah, this is how I plotted it. I did log. Are you saying
yeah, I
you
normally think
would normally only be log of like the y-axis?
no, I'm more thinking of it in terms of the way they use log in like complexity science and stuff, and to show scaling laws that don't adhere to normal distributions.
Mhm.
Yeah.
Yeah. So like what I did, like if you have like x cubed and you take the logarithm of it, then you could you can like bring the exponent down, and then you basically just have like the equation of a line, like mx plus b.
Mm.
And then like the m would be the slope of the line.
Mm.
So yeah, that's
Okay.
what I'm trying to show here.
Mm.
Yeah, so this is the code for just a single sphere. And if you run this, this is just with randomly generated points. So this is like the ideal scenario, just because
I see.
I wanted
Right.
to test it out,
Okay.
see what you would get, just
Mm.
with like a perfect case. And even with randomly generated points, there's like a lot of variation. If you run this like 10 times, you'll get like 2.9, 3.1, exactly 3. So I realized you need to do like a ton of measurements to actually come up with any meaningful conclusion. So what I did, I so this is the same code for the single sphere here. I just removed the visualization so it wasn't crashing my computer when you did it so many times. But all this does, it calls the original sphere function inside of a parallel table. So it just draws the spheres over like a giant 3D box shape, basically. And the spheres are overlapping. And this just plots all of the results. So this is what it looks like. Um, so this is with randomly generated points again. Uh, you get this. So you get quite a large variation between measurements. So the x-axis, this is sphere number. So it's just arbitrary. It's just the order that the sphere was measured. And then this is the scaling exponent. So it fluctuates quite a bit between like 2.8 and 3.2. But if you take the median measurement, you get like exactly 3. So like 3.000. And then the derivative, you get like 2. And also the derivative, it's approximated quite a bit because like n of r, it's not a continuous function. So as you grow the sphere, you might like n of r might remain constant for like 10 time steps. And if you just subtract the difference between the steps, you'll just get 0. So to get the derivative, I used like a much larger like difference than n of r. So yeah, if
Yeah,
you
that makes
plot it,
sense.
yeah. So yeah, if you plot it, you'll get basically the same thing as above, just a bunch of lines with slopes of 3. And this is the derivative. It's a little wobbly, but yeah, if you fit lines to this, you get basically lines with slope of 2. Um, yeah, so now I went ahead and tried to do real measurements on the data. So the way I did this, the location I chose was not really rigorously determined at all. I just uh, selected a large area that looked somewhat uniform. So this is the projection of the data set in the 3 planes. And it's loading. What I did, I made another function that lets you put in like coordinates of a box, and then it will draw the box on the data. So this is the region I chose.
It'll extract out like a box of points.
Yeah, so it will draw like the grid of spheres like over this. So this is like a 3D region, but it's just projected into each of the planes.
Mhm.
Um, and yeah, also I had to figure out like what radius of spheres to start with, because if it's too small, there will be like no galaxies in it, or there won't be enough to uh figure out the derivative or fit a line to n of r. So I just made the nearest neighbor function, and this gives you the probability of encountering another galaxy a distance r away from a typical point in the data set. So yeah, so based on that, I set the minimum radius. It would be like a little bit off this chart, but yeah, I set it to 3 times 10 to the 8 light years. And yeah, this is my results for the smallest scale measurement. And this, I would say this is probably like the best results I got. So yeah, it looks like this. Yeah, we get median exponent of 2.94, in the derivative 2.00.
And this is for search spheres of a different location. So this
Uh,
isn't just completely always centered at Earth
no,
at
no,
the
this
center of the
is just
data
like
set.
this is just like the arbitrary grid that I chose here.
Hmm.
So,
Oh, these are
yeah,
3 views of the same grid.
yeah, this is the grid drawn in each of the planes. I
Hmm.
tried doing it all at once in like a 3D visualization, but it was just like crashing my computer. So this is the best I could do.
Hmm.
Uh, yeah. And yeah, so I set the minimum galaxy count to, I think, yeah, 350. So you can see it just cuts off here and doesn't consider anything else. Just because it came up with very poor fits below that threshold. Um, yeah, I think that's everything. Yeah, oh yeah, here's the plots. So this is n of r, the slopes. And then the derivative looks really crazy. But if you fit the lines to this, it's still like median value of 2.
So
So
that means that so the n of r, the delta, that would be the surface area of an expanding sphere, essentially.
yeah.
It could be thought of that way. Um,
Yeah, I think so, yeah.
mhm.
Um, yeah, so then I went ahead, using the same region, I started increasing the radius of the starting sphere. So yeah, I increased the radius, which gives you less spheres. So here, with the starting smallest radius, it gives you around like 600 spheres total. And yeah, I started at the maximum radius of the previous one. Um, and this gives similar results. So you get 3.02 for the n of r and 2.09 for the derivative. And this is what the plot looks like.
This is interesting. Oh, that's the galaxy count,
Yeah.
and you're moving the center of the space.
Um, no, it's the same sample space, but the locations would be adjusted to like accommodate the different size radius. So it's like the same confined box, but like different sized spheres filling the box.
Okay.
Okay.
I'm just
Yeah.
trying to get the why is there a pattern in the galaxy count? Because that's really interesting.
Yeah. Oh, yeah. I thought that was very interesting too. Um, I think it is just because the distribution of the galaxies is not actually uniform. So like if you look at the
Right.
like this, it looks like it's just like a dense box. But if you were to zoom in on that, it's not actually uniform at all. And
Yeah, yeah. The
as
data
you
set is has
and
has a
yeah,
sporadic volume.
as you increase the size of the spheres for each measurement, it it becomes like more and more noticeable. So you're like capturing more of the non-uniformity basically. So you get more of like clumped regions inside the spheres.
Right. So there's going to be a natural variation, but I guess what makes it a pattern in that plot, if we can.
I have no idea. It would so
But
yes,
well, so I mean, you have this grid of samples, right?
yeah.
Like in a
So
row and column, and then like in a three-dimensional array. So when you're indexing through that,
yeah, so
and then like it'll cycle back to
it's
the
totally
left
dependent
row.
on the x-axis. So yeah, this is the same thing. This is just sphere number, so it's just like
Hmm.
the order that the function measures the spheres in. I'm not sure exactly like what order it would be, how the table function would index it. But yeah,
So
just
this is interesting. So is that yeah? Because Sam is asking the question if the pattern is an artifact of indexing.
yeah, yeah.
Yeah, because do you know if they use Postgres as the database, as the underlying relational database?
For what?
Uh, for the because these are these the index numbers straight from the SQL query that you retrieve from the
No, no.
database?
So
Oh,
this is
okay.
just so the way I did the measurements, I have the original function that measures a single sphere, and then the way I set up the grid to be measured, I called it inside the parallel table function in Mathematica.
Mhm.
So that will just that gives you just like a three-dimensional grid of coordinates basically.
Okay, so this is an artifact of the computational universe.
Yeah.
Yeah, it's I mean, in a three-dimensional embedding, so you have like this all these galaxies, and they're spread out, and it's not uniform. So you're trying to like measure like density of this thing, and it's
Yeah.
wobbly. And so
Yeah.
if you put your samples in a row,
Mm.
and it gets like hot to cold along that row, and then on the next row it jumps from the start to
Yeah.
from the end to the start again,
Yeah, that's exactly what's
then you're
happening.
reading off those values. So like the
Yeah,
plot
so
would jump.
the actual order of measurements is like completely meaningless. Like
Mhm.
so it would be determined by a parallel table function. So I'm not sure how this generates or in what order it generates the coordinates, but it would be determined by this.
Makes sense.
Yeah. Um yeah, so yeah, from here on I just keep increasing the sizes of the spheres. So the next one we're down to like 200 spheres over the entire box, the same box. And now it overall the exponents tend to increase from here as you increase the size of the spheres and decrease the number of spheres. So here we're at like 3.18, 2.24 for the derivative. And yeah, you see the galaxy count once again. It's very patterned.
Mhm.
But
But no, so this is interesting. So you're saying that here it's growing a little bit more than cubic
yeah. I
for
don't know
and wait, are these for a certain number of samples in your sample set in that
why.
right grid?
Yeah, so in each sphere, yeah, you'll see there's less spheres, but in each sphere there's much more data points. So like we have like 10,000, 15,000 galaxies, and the highest one is like 30,000. Um,
Yeah,
yeah,
that's interesting. because you're in this like the sample is non-uniform, like all these points that we have to work with. So if you drop
No,
your sphere of
yeah, you could have the same size sphere and then shift it over and have like 0 galaxies
right,
sometimes. Yeah, like the range in galaxy counts is like massive. It's like between like I think like 500 and like 30,000. So yeah, that's why I think the like on like the large scale measurements are not the way to go. Like, it's not that meaningful. But if you zoom in like on my first measurement, the galaxy counts are like much more uniform. But also for smaller measurements, it's like the most like computationally intensive. So I don't think I could make the spheres much smaller and have it be reasonable to compute it. But what I could do, I could like get more samples of galaxies to like add to the data set. And then I could possibly increase the sphere size also. Yeah, so I just kept increasing it. So here we're up to 35 spheres filling the same box. Um, and then yeah, the exponent's like 3.5 now and 2.5 around there. Um, yeah, 150,000 galaxies.
how many
And
galaxies are there total? And the
in I don't know how many are in the box, but in the whole data set there's like 2.8 million.
okay,
Yeah. Yeah, if you were to add all of the numbers, but yeah, you're still getting like mostly uniformly straight lines.
yeah, yeah.
And I think this
When you
was the large,
aggregate hundreds of
yeah.
galaxies, that's
Um,
reassuring.
I think this is the largest. Yeah, this is the largest one. So this is using only 6 spheres filling the whole box. So we get 3.55 and 2.7. And yeah, we have one of one sphere that's all the way up at like 5. But also like very few galaxy counts. So that's probably why.
Hmm.
Um, yeah, and then this was basically the goal of the project here, and then I had a bit of extra time, so I decided to just place like a single sphere at the origin and grow it over the entire data set and see like what would happen. Obviously, this is not it's not a very good measurement just from our tests with the single sphere earlier. There's a lot of variation. So this was just like just for fun basically. But this is what it looks like. Um, this is also like kind of deceiving because it was very approximated. Like the step size on this is huge. Otherwise it would take like ages to compute this. But yeah, this is what it looked like. And then I
Well,
was
wait,
curious.
what's the horizontal axis?
This is R in
Oh,
light
right.
year. Yeah. So this is like N of R and R just centered at the origin
Hmm.
growing over one sphere. And then yeah, I looked on like a log plot again, and it looks like linear almost. So I decided to try and fit lines just to different sections of this plot, and got some very strange results. So this is like from the first section. Yeah, this is from the earliest part of the plot. You get a slope of like 1.8, 2.2 as you go up the plot. But I wouldn't take these results too seriously. It was just for fun.
Well, it's
Um,
interesting because on a general point set, um, you can imagine. So the distribution of galaxies is sort of it's very strange.
Very non-uniform.
Very non-uniform, and so you have like these structures of great voids, and
Yeah,
then
yeah.
sort of on the periphery is all these clustering up of little local galaxy
Yeah, yeah.
clusters, things of that sort. So, um, you'll have like local bands of like wispy strands of a galaxy formation or
Yeah,
clustering, I guess, and those would have locally, you know, smaller dimensionality as point sets.
yeah, yeah.
You know, if you see a bunch of galaxies all in a line, and you did this measurement locally to there, you would get like one-dimensional
Yeah,
on
yeah.
average.
Yeah, I think the smaller spheres are definitely the way to go here. Yeah, yeah, that's all I have for you guys. Yeah.
Very cool. Let's see if there's any questions from chat. Okay, so Sam is asking, highly recommend using Gaussian kernel smoothing to create an interpolation function for this field of local dimension values.
Gaussian kernel?
Yeah,
I have never
this
used.
will this will allow you to smooth out a lot of the noise.
Oh,
And then yeah, so he was actually mentioning here earlier that he said the dataset might be perfect for some sort of Gaussian kernel smoothing to look for large scale trends versus position. So
yeah, definitely try that.
hmm,
But yeah, I have never used that.
kernel smoothing. Yeah. Then the question is here, is this because the data is sparse near our near our location where R is small?
Um, yeah, so definitely the closer regions where R small is more dense, but I would not say it is uniform. So it looks uniform here, but clearly, like just from plotting Inavar over the whole data set, you see that it's not. And even though we didn't use the clustering algorithm for the actual results, like I think it is basically picking out the clusters, so you can see it is not uniform.
Hmm. Yeah, it's very interesting. I don't know where was there was some results that came out this year, I believe, where they had figured out that there's some super gigantic structures in the universe which didn't adhere to the concept of like the Big Bang or something like that. Like there was some contradictory evidence that there were structures that theoretically don't fit the theory of how the universe expanded because the structures were so large and like spread
Oh,
throughout many like a much larger portion of the universe had some kind of like structure. Pardon my lay wording for that, but
yeah,
there was some results that came out this year about that.
it's super interesting. Yeah, I will check it out.
So that would be like structures that were present before the inflationary period or
It had
something like
something to do
that,
with
and
the
they
Big
get
Bang, but I think it was just generally it doesn't fit the models. Like whatever models we use for how large a structure could be in the universe, they discovered structures that were way larger than that, which didn't fit any of the models that we use, which just shows you there's a lot still to be discovered in the cosmos. Cosmology is still ripe for a lot of discoveries, I think.
Oh yeah, yeah,
for sure.
I agree.
This is very cool. Is there do you have higher res versions of this that people can play with, or was this like the
Yeah, yeah.
one capture that you
Yeah, so
managed to get?
in my community post, if you just click, so this is not in the community post. This is like the actual like rendering in Wolfram, but this is a Google Drive link. If you just click on it, it will you can zoom in
Oh, very cool.
high res.
Nice, nice.
I might grab that for a thumbnail wallpaper for the institute.
This
Very
one,
nice. Yeah. What I like about this one is you can actually spin this one around in the community post, right?
Not in the community post. It's just like a bitmapped image. Because yeah, it was really hard to fit all of the stuff within the size limit in the community post. I had to like bitmap everything. But yeah,
So this one you can spin.
this one, yeah, you can spin if you actually like get the data set working, like in your own version of it.
Okay.
But
Oh, so the community, do you mean like the cloud version won't have the data set in the back to
no,
be
yeah,
able
the
to
cloud
render it?
one you would have to download the notebook and then download the like my file from Google Drive, and it should, if you just import it in like the first line, it should be working.
Very cool.
Yeah.
Quick question here. How are galaxy counts within spheres analogous to fractional dimension of space itself?
That is a hard question. uh,
Maybe Nick can also comment in here. I think part of the motivation for the fractional dimensionality is that it could be considered experimental validation for some of the stuff that we were looking at in the physics project. So I believe that's part of the motivation here. So if we think about the maths behind it, is the idea that if the count, let me think about this. Oh,
Yeah, you want to count the volumes of growing spheres, and if that increase in volume with respect to R has a quadratic nature or a
yeah,
cubic nature.
not so much the galaxy count. The galaxy count is not very important. You just need like a minimum amount of galaxies. But what's important is innovar. So
Mhm.
innovar, yeah, it has to grow.
And so that's the number within a radius R.
Yeah, so if you have a sphere at this size and you have this many galaxies inside of it,
Mhm.
that would be in of whatever radius. So you grow it, and then you count again how many are inside.
Right.
Like the
And
derivative would be like the change between sphere sizes as you grow,
mhm.
like the new radius, the new or the difference in galaxies, basically.
and sort of the assumption that makes it work is that the points inside are more or less uniformly spaced. So counting the points counts the volume.
Yeah, yeah,
oh, interesting.
yeah.
So if you get like clusters where it's more dense of points
Hmm.
and you integrate past that, then you're gonna pick up like a sharp increase there.
Yeah.
Um,
That's why, yeah.
so yeah, the point set is
spheres,
has non-uniformities in it. Sorry.
Sorry, say that again slowly.
yeah. That's why you like with the larger spheres, you'd get like higher exponents because when it's larger, you're capturing like the large scale structures of the galaxy. So
Hmm.
on a local scale, like on the smaller scale, the data set looks uniform, but as you zoom out, that's when you see all the clumping of everything. Yeah,
Hmm.
on a higher scales of R.
Makes a lot of sense. Cool. Any comments from Nick while he's here? Or any
No,
additional
no, I don't
questions?
have any. I was too
Okay.
late. Sorry, I missed a bunch of that. But sorry.
No,
It's a
no,
cool.
yeah,
I like the plots though. I'll definitely play with them.
very interesting. Yeah, so great. Thanks for that, and thanks for putting the effort of having the high-res versions of this that people can download and explore. And again, this is what's amazing about these types of projects is you can literally go to the link, it's in the description of this video, and you can play with it yourself. You can be a cosmologist from your laptop, which is pretty cool. So yeah, thanks so much for that, Lou, and
No problem.
great. Okay. Thanks everyone for tuning in. And yeah, maybe Dugan, do you want to give us a highlight of what we have planned for next week on live streams?
Yeah.
Just a quick
Yeah,
reminder
next
to
next
everyone
week we have next Thursday we have Nick doing qubits in phase space.
That's exciting.
Again.
We also more qubits. You can never have enough qubits. We're also going to be doing some design review on our hypergraph packlet, and that's exciting because Stephen's going to be joining for that one. So that'll be interesting. In probably more ways than one. And then also just to bring up that on the Wolfram channel, there will be some lambda exploration. So for those of you who are really into the computer science world, lambdas are the perennial favorite thing to ponder there. So yeah, be aware that will be coming on Friday next week. So we'll post about that from the Institute as well, so people can join that live stream. Otherwise, NK's book club on Sunday, and please start signing up for the winter school. Applications are soon to open, but you can start signing up for the newsletter on wolframinstitute.org. And yeah, if you really like this stuff and you haven't joined us for a summer school or winter school yet, then this is the kind of fun stuff that Luke has done here that you would be able to participate in. So yeah. Okay, thanks so much, everyone. Thanks for that presentation, Luke.